Okay, so welcome back. As you can see, I've decided to spice up my lectures by changing the background. I figured, got the capability with the iPad, might as well make use of it. Hopefully, everyone's eyes will be okay. So where were we, or what did we do last lecture? Well, we introduced induction. Okay, so this was a great tool which let us prove things about statements about all natural numbers. So infinite number of statements just kind of in a couple steps. So what I'd like to emphasize is that induction can be tricky. So it's an amazing tool, but you don't want to misapply it, because then it's very easy to lead to wrong statements. Okay, so the point is, with great power, as we know, comes great responsibility. So let me prove a statement to you by induction, and hopefully this will show you how you can how it's easy to make mistakes with this tool. Okay, so here's going to be the theorem. All cats are the same color. Okay, so that's what I want to prove. Let me just tell you a corollary first, before we get into it. So the corollary is all cats are black. The proof of the corollary, well, it just follows immediately from the theorem. Plus, I need one additional fact, plus the fact that I have a black cat. Okay, and so since all cats are the same color, and I have a black cat, I get the proof. Okay, so I'll put the proof symbol there. Oh, I should put, this should be my proof symbol, obviously. All right, so let me move this. So, how do I want to prove this theorem? Well, I will use induction, okay? And I'm going to prove that actually this statement, for all n, any group of n cats are the same color. Okay, so this is obviously enough to prove the theorem that all cats are the same color, because there's only finitely many cats, as far as I know, in the world. Maybe I should say on Earth. So, if I can prove this statement that for all n, any group of n cats is the same color, then all cats will be the same color. Okay? So that's the proof. So let's do so how do we want to prove it by induction? Well, the first thing we check is the base case. And this one turns out to be pretty easy. So what's P of 1? Well, I'm taking a group of one cat. Sorry, so maybe I should call this P of n. So I'm taking a group of one cat, and it's the same color. And it is the same color as any other cat in the group. Okay, that's perfectly true, right? I have one cat. I'm only going to be able to see one color there. Okay, so now let's do the induction step. So I'm assuming it's true for P of k. So P of k is true. And I need to show P of k plus 1. Okay, so I'm assuming this and show this. Well, let's count out the cats. Okay, so I'm taking a group of k plus 1 cats. I should have practiced how to quickly draw cat heads here. So that's going to be 1 cat, 2 cats. Then I have I'll just say the kth cat and the k plus first cat. So 1 cat, 2 cat, up to kth cat, and then I have k plus first cat. Okay? And we want a goal, so our goal now is to prove they're the same color. Okay, so what can we use here? Oh, well, we want to, at some point, whenever you're doing an induction proof, you need to use the fact that P of k we're assuming to be true. So what we know here is, by assumption, the first k cats have the same color. Okay, so if I look at the first collection of cats, these are all one color. Okay, and now what do we know next? Well, not only do the first k cats have the same color, but if I take any group of k cats out of this k plus 1, or collection of k plus 1 cats, they'll also be the same color. So I can look at this collection of cats. These are all the same color. Okay, so let me just write this down. So if I have cat 1 up through cat k, all the same. And then if I have cat 2 up through cat k plus 1, these are all the same. But look, I said that 1, so cat 1 is the same color as, cat 2 up through cat k. But these are all the same color too. So 1 and k plus 1 are the same color, and therefore every single one of these is all the same color. So cat 1 is the same color as cat 2 up through k, but cat k is the same color as cat k plus 1. So therefore, every cat is the same color. And therefore, by induction, I get that the statement is true for all n. So what we just showed is P of k implies P of k plus 1. So we're done. Okay, great. That was a great lecture. See you tomorrow. Or Friday. Or maybe I should do, okay, what went wrong here? Okay, so I think what I'm going to do is, I really would like people to think about it for more than like my usual pause break. So I'm just going to delay this until the end of the lecture, okay? But think about it, and then, of course you can just go on YouTube and go to the end of the video, but I would really encourage you to think about what went wrong, okay? Okay. So let's go back to functions, okay? So what we're really going to start talking about now is cardinality and counting sets. And we see this a little bit with finite sets, but we're going to be now switching gears a little bit and trying to apply the same ideas to counting infinite sets. And the best way to do that is through concepts that we've seen before, injective and surjective functions. So remember, we have a function from a to b. Well, it can be injective or surjective, right? So the first is saying that if I give you two different inputs, they produce for you two different outputs. So we have some picture like this. Surjective was saying every thing in the range was the image of some element of the domain. And then if you put these together, so injective plus surjective was bijective, in which case you have this complete one-to-one correspondence between elements in your range and elements in your domain. Okay, so what is nice about these functions or these features is that you can use these to understand the size of finite sets. This is essentially what we've seen in the pigeonhole principle. So if I have finite sets A and B, I don't know if I've used this notation before, but I'll use A, B, cardinality of A and cardinality of B less than infinity. So if there exists an injective G from A to B, well, this is equivalent to the cardinality of A being less than or equal to the cardinality of B. Okay? If there's an injective function from A to B, A has to have less elements. Similarly, if you have a surjective H from A to B, this happens if and only if the cardinality of A is greater than or equal to the cardinality of B. Notice this isn't, completely obvious. I mean, you have to, if I give you two sets A and B, and you know, for example, that the cardinality is larger, well, you still have to come up with this surjective map. But it turns out that you can kind of always do this. You can always assign an element of A to an element of B, though it might not be obvious how to define it. Similarly, or if we're just putting these together, there's some bijection from A to B. Well, this happens if and only if cardinality of A is equal to the cardinality of B. Okay, so now we're really going to get into a kind of a revolutionary idea, which is to try to apply the same ideas for finite sets as to infinite sets. So while the number of elements of an infinite set doesn't really make sense, we can still use the above idea to get some sort of understanding of size. Okay, so when you have infinite sets, we don't want to just say, well, the cardinality is infinite. It's going to be useful for us to say that there are more, that one infinite set is larger than another infinite set. And the way that you do that is just by defining analogs here to get some understanding of the relative size. Okay, so how do you do this? This is, Okay, so now we're into a revolutionary definition. which was, I guess I was going to say George Cantor, but I can just say Cantor. So what this says is that two, I guess, okay, so I'll just say two sets. So, they're going to be, it works for finite sets too, but I'm thinking of these now as two infinite sets, are said to have the same cardinality. And I'm going to write this as just the cardinality of A equals the cardinality of B. Of course, cardinality, what I've said so far, I haven't really introduced more notation than just a finite number or, infinity symbol. But, well, we might see some more notation for this now. But now I'm just saying these have the same cardinality if there exists a bijection between them. Okay, so it's kind of naive. It's exactly taking something for infinite sets, or something for finite sets, and applying it to infinite sets. So if there exists a bijection from A to B. And we're going to do, similarly, we can say cardinality of A is less than or equal to B. So if there exists an injection, G, from A to B, we say the cardinality of A is less than or equal to the cardinality of B. So I'm going to leave off the search activity statement for a little bit. You'll see kind of soon why I'm doing that. So let's just do some sanity checks. Does this definition make any sense at all? Or does it correspond at all to what we think about with cardinality of finite sets? So here's one thing to check. If the cardinality of A is the cardinality of B, and the cardinality of B is the cardinality of C, then is the cardinality of A equal to the cardinality of C? Okay? So for finite sets, this is true. If they're the same, if these have the same size and these are the same size, then you automatically get this, that the other two sets have the same size. But remember, now we're using a kind of different definition, and we have to check that this works with this definition that we're using for infinite sets. But this is true, so this is yes. And the reason is that a composition of bijections is a bijection. Okay, which is nice, right? So if I have, so this assumption is telling me I have a bijection from A to B. This one is telling me I have a bijection from B to C, and therefore, since I can take the composition of those, and I get a bijection from A to C, so they have the same cardinality. So F1, F2, and switch to the order, F2 composed with F1 is my bijection. Okay, so now let me do another sanity check. Sanity check number 2. So this says, well, if I have the cardinality of A less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then is cardinality of A equal to the cardinality of B. So again, this is something that for finite sets we can work out easily, right? But how about with this definition? So first, what do we know? So we're given an injective function, G1, from A to B. And we're also given an injective function g2 from b to a. And what are we supposed to do with this? Well, what we want to do is we want to cook up a bijection f going from a to b. And this already, so our second sanity check is showing us that this is that we're slightly insane. This is not obvious at all. It turns out to be true, and it's called the Cantor-Bernstein theorem. I think we'll probably see a proof of it, or part of a proof of it at some point. Okay? But this is already, you can kind of see that this is going to be a trickier notion than with finite sets, because you have to get good at constructing functions from information that doesn't immediately tell you how to do this, right? So if there are finite sets and you know that, this cardinality of this is smaller and this is smaller, it's pretty easy to work out a bijection between the elements. But here it's trickier, okay? So let me give you an example, okay, to kind of show you that the Cantor-Bernstein theorem is definitely non-trivial. So I'm going to define two sets. These are going to be sets in the xy plane. Okay, so these are, the first one is xy in R2, where the square root of x squared plus y squared is less than or equal to 1. And the second set is, I'm just going to say it's negative 1 to 1 times negative 1 to 1. I can write this out. This is xy in R2, where the x coordinate is less than or is between negative 1 and 1, and the y coordinate is between negative 1 and 1. So I can draw the picture of this. This is the first set. A is just the unit circle. So here's 1. And then the set B is the unit cube. And now I'm going to define two injections. So I have two injections. So the first one is pretty easy. As you see, the unit disk inside the xy plane, so I forgot to label it, that's my set A, is contained in the unit cube, or the unit square. Okay, so the function xy goes to xy is an injection. So you just do the identity map on A. Since A is already sitting inside of B, you get that that's an injective thing. Now what do you do for B? So that's G1. For G2, which goes from B to A, well, you just shrink the little cube a little bit. So you go from xy goes to x over 2, y over 2. So you're just shrinking the coordinates by half. You can check that this is contained in the unit square. My picture is getting a little muddled, but that's the image of B. Okay, so this is a perfectly good function from B to A, and it's easy to see that it's injective. Okay, just because, well, if you had two things that get sent to the same element here, you multiply element by 2, that's going to give you an inverse, and you get that it's has to be a unique input there. So what does this mean? So I have two injections. I have an injection from A to B. I have an injection from B to A. So Cantor-Bernstein implies a bijection. But what is this? This is not obvious at all. Okay? So you get so it's a really, a wonderful theorem. It's very easy to define these two injections, and then you get something which, if you were trying to, define this injection, or this bijection, by hand, you'd have a pretty difficult time, okay? But the Cantor-Bernstein theorem just says that you can do it. Okay, so I'd like to now give you one of the main definitions for the next couple days. Or really, just the main definition of the class, I would say. So we think of the natural numbers as kind of the most basic infinite set. And so we'd like to characterize the infinite sets that are similar to the natural numbers. So we say a set A is countable if it is finite, or the cardinality of A is the cardinality of the natural numbers. Okay, and just remember, so this means there exists some bijection from N to A. Okay? So let me do a couple examples. This is going to, as I said, at least for the next couple of days, this is going to be one of our main focuses. So let's do some examples. So the first one is that the cardinality of the natural numbers is the same as the cardinality of the integers. Okay? So what this is saying is Z is countable. So I'm going to not give you the formal bijection. I'll just draw the picture. So we have the integers here. So 0, 1, 2, 3, and so on. -1, -2, -3. And really, you should think of this definition of countability as saying, well, if I have this bijection from the natural numbers to Z, I'm really just counting Z. So here's going to be my bijection. I'm going to send the first element of the natural numbers 1 to 0. Then I go to 1. Then I go to -1. Then I go to 2. Then I go to -2, and so on. So there are a bunch of different ways to show that the cardinality of these sets are equal. This is one. So just as a little exercise or warm-up, define the bijection. Okay, so you can actually just use kind of this picture that I've indicated to tell you where the natural numbers are going. And you can actually write down a formula in this case. Okay, so define an explicit bijection from N to Z. So let me give you another example, which I think is more surprising, which is that the cardinality of the natural numbers is the same as the cardinality of the natural numbers times the natural numbers. So, when I first saw this is just, mind-blowing. This seems so much larger. Right? Not only, you have this is like an infinite collection of different natural numbers, right? It's like saying it's looking at the real numbers versus the xy plane. One of those seems a lot bigger than the other. Okay? So how can you do this? So let me just draw you a picture of how to visualize the natural numbers times the natural numbers. You can do it inside the xy plane. So you start here. You put the natural numbers on both sides. So 1, 2, 3, 4, 5, 6. And then what you do, I mean, the natural numbers times the natural numbers are just identified with the these points in the grid that have these coordinates. Right? So this is drawing too many dots now. So this goes off in both directions. So this is, you're filling out the unit grid inside the xy plane, or a quarter of the xy plane. Okay, so these are the coordinates mn, where m is in n and n is in n. And now how do you define this bijection from the natural numbers to this, infinite grid? Well, it's kind of similar to what you do for the natural numbers times z. So I'm going to start here. This is where I send 1. Then I go up the grid. That's where I send, so this would be like 1, this would be like 2. Then you go over, then you go over, and you just start sweeping out these diagonals of the of n cross n. So you go up and over. So this turns out to be a bijection. Even this is very hard to work out the formula, or pretty hard to work out a formula. So actually, at some point, I think we'll prove that if you have like a product of countable sets, it stays countable. So it's better to have a proof than just this picture, but I think the picture shows you what to do, right? And you can see that it's going to be surjective because these diagonals are hitting every possible combination. It's injective because the path that I've traveled upon never crosses itself, right? That would be kind of a failure of injectivity, would be if I, swept across, but I never do. Okay, so we will see much more of this. And, at some point, what we're going to see is that there are sets that are uncountable, where I can't do this trick of, or somehow there are these sets that I can never try to work out these snake-like patterns to fill out the entire set. Okay. So now I think I'm going to go back to cats. Okay, so cardinality will be tomorrow and the next couple days. Let me go back to cats. So a usual problem with induction is the base case. Okay, so this is just something to be aware of. So it's not the problem here, actually. But whenever you're doing an induction proof, sometimes it's very easy to convince yourself that you have something completely correct, and then the problem is just like the base case, which is supposed to be the simplest, turns out to be false, and everything breaks apart. Okay, but here the base case is good, right? Because we had one cat, and it's the same color as itself. So therefore, the problem has to be in the second case. So the implication P of k implies P of k plus 1. Maybe I shouldn't say the second case, the second thing to prove. Okay, so let me break down just one thing first. I'm going to do one particular case, P of 2 implies P of 3. And then we'll see where the problem is. So this is actually going to be okay, but we'll see where the problem is. So remember, now we have 3 cats. Oops, I'm forgetting how to draw them. Okay. And what P of 2 says that these are both the same color. And these are both the same color. So therefore, all the same color. Sounds great, right? I mean, this is, if these are both black, these are both black, then all three of them have to be black. On the other hand, now maybe we can see where our mistake is. We needed this cat in the intersection to be able to say that these two being both black and these two being both black, implied that these were the same, or these were the same color and these were the same color, implied that the first one was the same as the third. Okay, so now what happens if we want to go one step back and we want to show P of 1 as P of 2? Well, now we have two cats. We know that P of 1 is true, so each cat is the same color. But now we can see what the issue is. So in here we have, okay, this will be a red cat. This will be a yellow cat. P of 1 is true. Each one is the same color. But when there's two cats, there's no statement in the no cat in the intersection where you can try to transfer, this red to this yellow. So those can be different colors, and then that just destroys the entire induction, because you're going to have, if P of 2 is now false, so this turns out to be false, then you don't get P of 2 as P of 3 implies P of 3, P of 3 implies P of 4, and so on. Okay? So that is why cats are not all the same color. So, thanks. And